Hi guys. The biceps curl is probably the most recognizable weightlifting exercise. But did you ever wonder how much force your muscle actually has to exert in order to lift this heavy thing? Well, today, in this video, I'm going to show you how to compute how much force it takes for your muscle to do a bicep curl.
Okay, let's do a static, well, it's actually going to be quasi-static, as you'll see, biomechanical analysis of the biceps curl in order to see how much force the biceps muscle has to exert to lift a dumbbell. And along the way, we'll also see how much force is exerted on your elbow joint as a result. First, let's take a look at the muscles involved. There are 3 muscles responsible for flexing your elbow joint. The biceps brachii is the main one, but there are also 2 other ones involved, the brachialis and the brachioradialis, 2 smaller ones. So there are 3 muscles that are going to be working to lift that dumbbell. Now let's look at the elbow anatomy. The elbow is actually a pretty complex joint due to the fact that there are 3 bones joining together. We have a ball and socket joint between the end of the humerus and the proximal end of the radius, where it can pivot around that ball and socket. There's a hinge joint between the ulna and the humerus, and then you can see there's an interaction at that pivot joint between the radius and ulna. So 3 different joint surfaces are actually involved as well. So if we start looking at a free body diagram on our system, here's what we have. So we have the limb that's shown here as these white bones. We've got the dumbbell, and then we've got 4 muscle forces. Why 4? Well, the biceps brachii has 2 heads. It actually has 2 different connections to the forearm, which is why it's called the biceps, because it has 2 heads. So 2 biceps head forces, as well as the 2 other muscles involved. Now we aren't going to look at the force between the radius and ulna, so we've only got 2 joint forces. We've got the interaction with the radius and the humerus, and the ulna and the humerus. And all these are in 3D. So if you think about it, we're in trouble if we're doing statics, because the unknowns here, we know the dumbbell weight, we know the limb weight, we can measure the dimensions, but we don't know the joint forces or their directions, so there's 6 unknowns already. And we don't know the 4 muscle forces or their direction. So there's way too many unknowns for this to be a statically determinate problem. So we're going to have to make some simplifications. So first, let's assume that this is a 2D problem. This is going to help us a lot. So we're narrowing it down to 2 dimensions. We're going to eliminate a lot of those unknowns, those out-of-plane components, and reduce the number of equations needed to solve the problem. Also, we're going to do a single resultant muscle force. So this means all 4 of those different muscle forces are going to be grouped into one resultant force, and we're going to apply it at the location of the biceps brachii insertion onto the forearm. We're also going to assume that the joint force is a single force. So we're grouping the radius and ulna together into one rigid link, and so there's one joint reaction force that's going to push on the elbow in response to this motion. So that simplifies us down a lot. So let's put some more information down here. Let's look at some more simplifying assumptions. So we've got a 2D problem. We've got the single muscle force. We've got the single joint reaction force. But we also now are going to treat this as a static problem, even though there are some accelerations as the arm is rotating, as the elbow joint flexes. But we can assume that since the motion is slow enough, that the inertial effects due to the accelerations are essentially negligible. So we're going to break it up into discrete angles, and we do a statics problem at each separate angle in order to figure out these forces. So we can neglect the accelerations because we're moving pretty slow. We're also going to assume that the body forces act at the centroids. So if you look at this value FA, that's the force due to the weight of the arm. It's distributed along the entire length of the arm as gravity is acting on all of that mass, but we're going to take the entire weight of the arm and group it at its mass centroid. And then the same with the dumbbell. We're just going to apply the force right at the center of the dumbbell. We're also going to assume that the joint acts in compression only. Now this is a reasonable assumption to make because cartilage is so slippery and has such a low coefficient of friction that essentially all the forces acting on that joint are going to be mostly in compression, but there would be some shear and things as well to a smaller extent, but we're going to assume that just that compressive joint force. And overall, this is going to be an idealized geometry. I actually had to go to the literature to find some values, as you'll see, so that we would have all the information that we need to know. So this is the overall free body diagram, but let's put it in more of an engineering context. Okay, so here we go. Now we have our idealized geometry to represent this system. We have, I'm going to bring my pointer out here, the force due to the weight of the arm acting at the arm's centroid. We have the force due to the weight of the dumbbell, and here we have the muscle force from the combined muscles pulling up at that attachment point. Now that muscle force is acting at an angle alpha to the horizontal, and then here's my joint reaction force, Fj. That is acting at an angle phi with respect to the horizontal. And we're gonna find these throughout the course of the problem. And then here are the lengths. So LB is the length from the joint center of rotation to the attachment point of the biceps muscle. LA is the length from the joint center of rotation to the center of mass of the forearm. And then LW is the length from the center of rotation to the weight from the dumbbell. Okay. So, which of these values do we know and which do we not know? Well, we know the weights. I can go in and figure out from tables in the literature how much in general the forearm weighs as a part of your body weight. But we don't know the muscle force. That's what we're trying to find. We can compute the muscle force direction alpha, and I'll show you how to do that. But we don't know the joint reaction force magnitude or its direction phi. So, let's look at this. Here's our known values where the arm weighs approximately 2.2% of your body weight. BW is one body weight, one whole body weight. And so the weight of the arm is 2.2% of that. I got this from literature references you can see down at the bottom here. Let's assume that we're lifting a dumbbell that's 10% of your body weight. So if I weigh 165 pounds, it's a 16.5 pound weight, for example. But we're going to leave things general in body weight. And that way you could see when we get to the end and you see what the forces are in terms of body weights, you can estimate how much force it would take you to do this exercise. The length of the arm for a 6-foot male that I found in the literature is approximately 11 centimeters or 0.11 meters. The length from the center of rotation of the elbow to the biceps insertion on the forearm is 5 centimeters or 0.05 meters. The length of the entire forearm from the elbow to the center of the hand is about 36 centimeters. The length of the upper arm is going to be 30 centimeters or 0.3 meters. And then we're going to do this calculation at a set of angles from 0 to 90 degrees. And we also know alpha, as I mentioned, we can find from geometry. That's the angle that the muscle force makes with respect to the horizontal. And I'll show you how to calculate that. So this leaves our unknowns. Our unknowns are going to be the force exerted by the biceps muscle, that's Fm, the force exerted on the elbow joint or the joint reaction force, which is Fj, that's the magnitude of that force, and then its direction, phi. So we have 3 unknowns. We've got 3 static equations in 2D, so we should be able to solve this. Okay, let's start to put together the equations that we need to solve this problem. So first, I want to put together the equations that deal with the moment arm of the muscle and the direction of the muscle force, because those are both going to change during the flexion movement. So the moment arm and force angle. Okay, so let's look at the geometry here. So here's the center of rotation of the elbow, this dot. And so here's the arm. And then this dot is the attachment point of the muscle. And then let's say we've moved through some rotation theta. And here's the upper arm. That's got this length LU for L upper. And now once this thing goes through a rotation, this point of rotation or point of muscle attachment has moved to here. And so the muscle is always pointing from that point on the arm up to the top of the attachment point on the upper arm. Now put in another dotted line here, and then this angle we're calling alpha, the direction of the muscle force. Now this length from the elbow to the muscle point of attachment, we call it LB. And now what you see is this point, the point of attachment of the muscle, it's going to trace the arc of a circle here, right there. And so what I did is I just put in the location of this muscle attachment point here. I'm going to call that XM, YM, where XM is equal to LB cosine theta, and YM is equal to LB sine theta. And so if you work out the geometry, the moment arm, right, which is the perpendicular distance between that muscle force line of action and the center of rotation of the elbow, looks like this. And I'm going to call that D in the rest of the equations that follow. That is equal to LU LB cosine theta divided by the square root of LB squared times cosine squared theta, cosine theta squared, plus LU minus LB sine theta. And everything in those parentheses is squared. And that is the equation for the moment arm. So we're going to need that in our calculations. Okay, so the other thing that we're going to need is to keep track of that alpha, that angle that tells us the direction of the muscle force. Now let's look at that geometry. So here's my upper arm with my length LU. And let's say that here's my point of muscle attachment, my XM, YM. And now this arrow tells me the direction of where the muscle force is pushing, and then alpha is the angle here. Now we know that this length on the horizontal axis is XM, right? And then this length here, the longer side of it, if I look at this triangle, what I'm going to do here is actually look at this right triangle here in order to solve this. And so to do that, this length of the longer side of the triangle, of the right triangle, is equal to LU minus YM, right? So this tells me that alpha, the direction of the muscle as we move through this movement, is equal to the arc tangent of LU minus YM, that longer side, divided by XM. And again, for your records, XM is equal to LB cosine theta, and YM is equal to LB sine theta. Okay, so now we have everything that we need to start putting together the static equilibrium equations. So let's do that. I'm going to put this set of equations that I'm drawing next to this picture of the geometry of the free body diagram so that we can refer to that as we go. Okay, so let's get started. We'll start with the sum of the forces in the x direction, the horizontal direction. We only have two forces that have a horizontal component here because the weight of the arm and the weight of the dumbbell are both in the vertical direction. So we just have a contribution from the joint reaction force. And the way that I have it drawn here, we have Fj cosine theta, or sorry, phi, Fj cosine phi minus Fm cosine alpha, and that is equal to 0. So I'm going to call that equation 1. That's my sum of the forces in the x direction. Now my sum of the forces in the y direction. In this case, I have contributions from all the forces. I have a component of the muscle force in the y direction, the joint reaction force, and then both of the weights. So I have Fj sine phi plus Fm sine alpha minus Fa minus Fw, and those are equal to 0. I'm going to call that equation 2. And now I've got the sum of the moments about the elbow center of rotation. I'll just call that O as my center of rotation. That's going to be equal to 0. Give myself a little more room here. So now I have the moment due to the muscle force. That's giving me, the way I have it drawn here, it's going to give me a counterclockwise rotation. So I'm going to call that positive. And that's Fm times d. So you'll have to refer back to that d equation. We would plug that in to get the final values at the end here. And now I have the moment due to the weight of the arm. That's giving me a clockwise rotation, so it's negative. So I have Fa, and then the moment arm of that is equal to La times cosine theta. And now I also have a contribution from the weight of the dumbbell in the clockwise direction, so that's going to be negative, and that's equal to the Fw, the weight of the dumbbell, times the moment arm of the dumbbell, which is Lw cosine theta, and that's equal to 0 as well. That's going to be equation 3. Okay, so we've got 3 equations, and my 3 unknowns I'm trying to solve for my muscle force, my joint reaction force, and my joint reaction force direction. So first thing to do, I can look at this moment equation and notice here that this Fm here is the only unknown in this whole equation. Everything else in the equation we already know. So I'm just going to solve for Fm, and we've got our first unknown quantity here. So here's Fm. If I just move everything to the right-hand side and divide by the moment arm, I have 1 over d times Fa La plus Fw Lw. Both of those were multiplied by a cosine theta. And there we have our muscle force. So we've solved for our first unknown. Now, the other 2 unknowns to solve for are the angle phi and then the magnitude of the joint reaction force. So to do that, I can go one of 2 ways. I can I can try to solve for Fj first. I can solve for phi. I've got two equations. The tricky part is phi is tied up in these sine and cosine terms. So we got to try to take advantage of maybe some things we know about trigonometry to make that more easy to solve for. It does get a little messy, I'm not going to lie, but let's do it. Okay, so first I'm going to put equation 4, that's the muscle force equation here, into equation 1. So I'm going to take that Fm that I just solved for and put it back into that first equation. So then I have Fj cosine phi minus all this that gives me Fm and then we know that we also have a cosine alpha, that first equation, and all that is equal to 0. So now I can solve for Fj. It's still going to have a phi in it, but what we'll do is we'll solve for phi last, and we can always come back and put it back in. So here's my Fj equals to 1 over d times Fa La plus Fw Lw cosine alpha cosine theta, and then all this gets divided by cosine phi. Okay, so the only unknown in this equation is this phi, and so the last thing to do is to solve for that phi, and then we can always come back and plug it in to this equation. So I'm going to box this equation for Fj. I'm going to call that equation 5. Okay, so the last thing to do is to solve for phi. This is the algebra is getting a little long, but let's do it. So basically what we're going to do is we're going to take equation 4 and equation 5 that we just found, and we're going to put those into equation 2. So this way I'll have I'll put my Fj and my Fm into equation 2, and then all I'll have left in that equation to solve for is phi. Okay, so let's do that. I'm going to take equation 4 and equation 5, and I'm going to put those into equation 2. And it's going to look like this. 1 over d times sine phi over cosine phi. I went ahead and pulled those out and grouped them together because that's going to give us a tangent, right? Times Fa La plus Fw Lw times cosine alpha times cosine theta. So that was my component from that muscle force equation, plus 1 over d. That was my Fj in that first term. Here now, here's my muscle force. And that's times cosine theta times sine alpha. My last two terms, I've got my weights minus Fa minus Fw from the barbell, and all that equals to 0. All right, so let's see what we can do here to clean this up. I want to get phi by itself, right? I'm trying to solve for phi here. So let's move some things around. I now have, let's move the, keep the first term on the left-hand side because that's got the phi in it. We'll move everything else to the right. So I've got 1 over d times, now we can change that sine phi, cosine phi to a tangent phi, times Fa La from the arm weight, dumbbell weight term, and that's times cosine alpha cosine theta on the right hand or left hand side, and we'll put everything else onto the right hand side, where I have FA plus FW minus 1 over D times FA LA plus FW LW cosine theta times sine alpha. All right, squish it in there. All right, so now I'm going to move everything else except for that tangent phi to the left-hand side. So I'm going to divide through by this 1 over D and all these terms to get to isolate that tangent phi. So that's my goal. So if I do that, I get this big, not too pretty looking equation where I have tangent phi equals to D times FA plus FW minus FA LA plus FW LW times sine alpha cosine theta, and then all that is divided by FA LA plus FW LW times cosine alpha cosine theta. Okay, so that is my equation. Now what I'm going to do is I'm going to take all of this, just to save some space here and some time, and I'm going to call that A. Okay, so this is this whole big thing here. That's going to be A, and then phi then is just equal to the arctangent of A. Okay, so now we have our phi in terms of everything here. So you can see up in this equation for phi, everything is known. There's no unknowns left in that equation. We have our equation for Fj here. And we have our equation for Fm on that same page. So we've got all three of our unknowns solved for. Now what I did is I went and I took these equations and I put them into Excel, and I just put a series of angles down a column, and then I just computed the value of Fm, Fj, and phi at each angle, so then we could plot it and see how these quantities change over the range of motion. And this is what the muscle force looks like. So you can see from 0 degrees where the arm is horizontal to the ground, up to 90 degrees where we've lifted the dumbbell all the way up to the vertical position where the forearm is vertical. You can see the force. So you can see the force is pretty high, 77% of your body weight. Maybe it's more, 78% of your body weight. So that means, let's say you weigh 100 pounds, your weight that you're lifting is 10 pounds. The dumbbell is 10 pounds, right? 10%. But it takes 78 pounds of force to lift it. And that's because of the lengths of the moment arms. The moment arm of the weight, right, from the center of rotation out to the dumbbell is much longer than the moment arm from the center of rotation to the muscle force. So the muscle doesn't have much leverage, so it has to exert a lot more force than the weight of the dumbbell in order to lift it up. Here's the joint reaction force using the equation that I showed you. You can see at the beginning here it takes 66% of your body weight to hold that weight in the horizontal direction, and going back here to the muscle force, you can see like the muscle force, the joint reaction force also decreases as you move through the motion. So the more you flex your arm, the less force it takes in order to create static equilibrium. And then the final unknown was our joint reaction force direction phi, and you can see how it changes here, where it's negative to begin with, and it's it's about 79 degrees downward. So that makes sense. If the muscle's pulling upward really hard, in order for this thing to be in static equilibrium, the joint reaction force must be pointing down when we start. And then you can see how that direction changes as we go through the motion. Once the weight moves into the nearly vertical direction, then the joint reaction force is almost pointing straight down to balance out that high muscle force. If we look back at the muscle force here, it's still 65% of our body weight when we get to 90 degrees. And so the joint reaction force is developed in response to that. But now let's have a little critical thinking added here. Now, if you think about it, how good are these results? And that's something you should always do when you do one of these problems is, how reliable are my results? So one thing we can look at is, okay, what about this range of motion? We're going all the way from 0 to 90 degrees, right? So from a horizontal forearm to a completely vertical forearm. But if I look at the motion of actually doing this biceps curl, your arm doesn't make it all the way to vertical. In fact, it stops about 40 degrees short of vertical. So it's only gone through a range of motion of about 50 degrees. So this means if we look at our graphs for muscle force on the left and joint reaction force on the right, really it only has any really true meaning from 0 to 50 degrees. So you can see that to the right sides of these graphs where it's kind of grayed out here, that data is kind of, I guess inconsequential or not important because we can't even get our arm into that position. So this is always a good thing to do, a good exercise to do, to think about my results, see if they make sense, see if they're reliable. Now, another point I'd like to make is we're looking at these graphs. Let me go back to the original graphs here. Why does the force go down? Let's think about that. Why does the force go down? Let's look at our geometry. Now, you can see as I move through flexion, the moment arm of this weight, this dumbbell, is going to decrease, right? The perpendicular distance between the rotational center and the line of action of this force from the dumbbell weight decreases as we move through the motion. But so does the moment arm of the muscle. And the moment arm is very small. So you might think, well, even though the moment arm of the dumbbell is decreasing, that really short moment arm is decreasing too. So you could think it might take more force. But what we can do is we can actually look at the how those moment arms change over the course of the motion in order to get a better idea about this. So let's see here. Now, I've plotted the normalized moment arms on the y-axis. Now, the moment arm of the biceps is the red one, and the moment arm of the dumbbell is the white one. And what you can see is that so these have both been normalized, which means they're both divided by their initial value. So you start out with a value of 1, and then you get down to their smallest value as we go. What you can see is that the moment arm of the biceps muscle decreases at a smaller rate than the moment arm of the dumbbell in a relative sense. So the further the distance is between these two curves, the less force it's going to take in order to create static equilibrium. But what you can see is now once these things start to get closer together again, that's when you see this change in slope where the muscle force is starting to reach kind of a steady state value, and you can see the joint reaction force doing the same. So it all comes down to the relative moment arms between external loads placed on the body and then the moment arms of our muscles. In general, the moment arms of our muscles are very small because we're built compactly. The muscles pass very close to the joint centers. but the moment arms due to external forces are quite large because we've got relatively long limbs compared to the moment arms of our muscles. So what you'll always see in response to that is the muscle forces and joint forces that it takes to move around and do all kinds of actions are much higher than the forces exerted on us by our environment. So that's my analysis of the biceps curl.
Hey, Eagle. Hey guys. I hope you learned a lot about static biomechanical analysis. Well, number one, the importance of relative moment arms between external loads and muscles makes a big difference in biomechanics. Number two, you got to make a lot of justified assumptions to get a problem in biomechanics down to something solvable with statics. Number three, critical thinking. Always take a step back and think about your results, no matter what you're working on, and you'll be better for it. I'm going home.